standard model, it shows the force carrier, so it doesn't line up completely with what it has in your standard model thing, because it's like what carries that force. That's in the standard model diagram you see. But these are the 4 forces, okay? Very important. So strong nuclear, electromagnetic, weak nuclear, and gravitational. Okay, so let's fill this in now. So a strong nuclear, this is the force that holds the nucleus together. And its range is only within a nuclear size, so it's only applicable to things at a nuclear level. Electromagnetic forces refers to the force of attraction or repulsion between charged particles. Now this can range, this is infinite, so it could talk about the charged particles at a nuclear level, or it can talk about, you know, something as big as a balloon and its charge repelling. Weak nuclear is the force that allows the transmutation of quarks involved in radioactive decay. And this, again, it's at a nuclear size. The force responsible for, and then gravitational is the force responsible for the attraction of 2 masses. Okay, and this is infinite, right? Because we can apply it to just very small, or we can apply it to the Earth and the Moon, right? Like it can be huge, or it can be very small. Okay? Now, here is where it gets cool. In order for physicists to have developed the standard model and study the nature of matter and all of its subatomic particles, atoms had to collide with one another at very high speeds. So high speeds are necessary because they need to overcome the strong nuclear forces and break the atom down into its subatomic particles. Okay? So we need very small particles, okay? Because if we had too big of a particle, like even an alpha particle would be too big. It has too much mass. Okay, but something like a proton or electron, we could accelerate it really quickly through something like the Hadron Collider, okay? And if we could smash it with another particle, we can break that atom apart and look at its individual parts, okay? So this is where we see the Hadron Collider. So I'll show you a news report about this.
Hadron Collider has been switched back on, as I said before. Thank God for it too. Scientists are waiting for the first new data to begin flowing from the underground particle smasher, paving the way to a new era in physics, possibly. So the big question is, what is this new era? Nanotech scientist Michelle Dickinson is here to tell us. Michelle, good morning.
Good morning.
Now, okay, first up, I love this kind of stuff.
Good, it's exciting.
It. Well, it's really, really interesting.
It's like the biggest car crash ever that you can control.
The fastest car crash.
It's amazing. It's the most energy we can do in a man-made thing. We're at speeds of almost the speed of light. We're at temperatures below deep outer space. It's awesome.
Okay, that's the upside. The downside is no one can see any of this happening.
Which is even better, right? Because it makes it almost magical.
If you want to see the biggest car crash in the world, you want to see it.
Well,
it's happening in a tube.
You can
the
see a
ground.
representation of it through the graphics and through the mass spec images that you get.
Oh.
But it's like nanotechnology, right? People will love nanotech. You can't see it, but it's still cool.
No, but also here's the other thing. This is why it's not like it, because nanotechnology is actually there, whereas the Hadron Collider is trying to find things that may actually never have existed.
But they're still there, so it's measuring things like particles and the mass of particles. It's working out the theory of relativity, whether E equals mc squared actually can exist for different supersymmetry particles. It's awesome.
It's a really, really cool machine,
Yes.
which is trying to look at things which are invisible.
It's 27 kilometres of machine, so it's a ring in which you accelerate protons so fast, and then you head-on crash them together. How awesome is that?
How do you like? You put a lot of protons in it, do you? Or just one? Because the graphic is like there's two, one going one way,
so
one
you do
going the
two
other.
beams, and
Two
then
beams.
you work out exactly where they're going to collide, and where they're going to collide, you have these detectors. They've got different detectors to detect different things, like the mass, like what's going on. And when you crash them together, you break down these protons into their subparticle parts. And so you see what flies off, and you work out whether or not it's real. That's how the Higgs boson was found in the last experiment.
Absolutely.
And we got to solidify the theory that we'd thought for a long time, that there is such a thing as a Higgs, or the God particle, the Higgs boson particle, that holds the rest of the particles together and gives things matter. So now we're going to go look for dark matter.
Of course. Well, it's the logical thing to do.
Right.
So you've got these two beams. So if you're the unlucky proton leading the way,
Yeah.
you know, because if I was there, I'd say, no, you go first, guys. I'll come up the back. So you've got these two. How do they get them to hit exactly? Because they're particles. They're tiny, laser beam, tiny, and they go kilometres under the ground at an extraordinary speed and hit each other square on. How do they do that?
Right, but it's all controlled in a tube, right? So it's in a big ring tube, so you know exactly where they're going to hit. We get 800 million collisions per second. So when we're talking about how many we're hitting
That's a lot.
There's heaps of data. Of that, only about 1,000 of those collisions per second are useful data that then we extract. It's a massive big data problem. If you look at the capacity that the supercomputers need to have for this, it's processing, it's being done around the world. It's incorporating scientists who don't talk to each other, scientists from Iran, from Pakistan, from India, who are all working together on one big worldwide project. I think it's great. Science is overcoming the politics of this.
I mostly don't understand what you're saying. Mostly.
Mostly. So,
Like the supercomputers, they only have to be super because there is so much information coming so quickly, am I
and
right?
it would take decades to process it if they weren't supercomputers, because we need the processing power not only just to save the data but be able to interpret it. And to do that, we take the data, we copy it, and then we send it around the world for scientists to interpret.
Okay, so with the Hadron Collider, when it first came up, it was hugely successful. I mean, obviously there were some teething problems. Off the grid for a couple of years while they modify it, and now it's just faster. It's exactly the same thing, but they can send these things at each other at a faster speed.
So we ran at 8 tera-electron volts, now we're at 13 tera-electron volts. We're about 50% more energy for hitting the particles
Why don't you
together.
just go double it? Why don't you just go higher?
Because I don't think we're at that point where we can not
That's
only
the hard
do
thing, is
it's,
it?
well, it's really hard when you look at the technology it needs to just accelerate these things. We're pretty much creating.
Look at if you look at your data sheet, she's saying that they're going so many tera electron volts. If you look at your SI units, tera is the very highest like value. Like so, it's huge. That's a huge amount of energy.
The Big Bang in a test tube.
Yeah,
so it's not like you can just throw in more energy, and there's also containment of that energy. So what we're doing now is we're hitting them a little bit harder together in the hope that, number one, we can see maybe more types of Higgs boson. Maybe they have a different way, because if you hit it more, you get the particles breaking off for longer, so you can do more of an experiment because they degrade really quickly, and you might be able to get new particles off that we've never seen before.
Okay, so, but you might not, because they might not be there, but we don't know until we do
We
this.
don't know, but we've been doing theoretical physics for so long. We have a lot of theories on what we will find, and you know, this is where the experiment proves if it's true or not.
What might, just finally, is it possible that something will happen as a result of the Hadron Collider that changes our lives?
I reckon so, yes.
What might that be? Now we're getting to the nitty-gritty. What might that be?
Well, first of all, if we can find dark matter or understand more about the energy of how our universe is held together, That would be cool. If we can work out what dark matter is, we might have to figure out whether there are parallel universes, which would be even cooler.
That would be very cool.
And also little technologies like the radio wave, for example. It wasn't called the radio wave because we didn't have radios, but radios exist because of the radio wave, which everybody's listening to
So some other
now.
great thing might be...
So an amazing thing that we don't even know exists could be created.
So it could solve global warming.
No,
it could. Seriously, we don't need to worry about global warming anymore.
I think we need to worry a lot about global warming.
Because here's the thing. There's a parallel universe. That one is fine.
I think New
So
Zealand
we'll just
should lead in the global warming research too.
I knew you'd say that. All right, Michelle, it's always lovely to talk to you. Thank you very much, Michelle Dickinson.
Okay.
Very fast talk.
Yes, yeah. But, yeah, I just thought it gives you a bit of an idea of, you know.
So you want to find, like, dark matter?
Yeah. Crazy, hey? I don't know.
Is that a thing between, like, the galaxies? I'm pretty sure it's, like, faster than the speed of light or something.
Is a hypothetical kind of matter that cannot be seen with telescopes, but accounts for most of the matter in the universe. The existence and properties of dark matter are inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. And like this stuff gets into things like string theory and craziness. Like we are just touching the surface of atomic physics in this class. Like it's just like, you know, if you had a plate of chicken parmesan, you just, you know, taste the tomato sauce. That's all we're doing, you know? Like that's it, right? Like we're just, like, there's so much going on. This is a huge field that's always changing. And so that part in the Symphony of Science where this guy's talking, this is his TED Talk that like those clips are taken from to make the show. So I'll just show you a little bit. It's kind of long, but we'll just watch 2 minutes. The first 2 minutes are the most interesting ones.
This is the Large Hadron Collider. It's 27 kilometres in circumference. It's the biggest scientific experiment ever attempted. Over 10,000 physicists and engineers from 85 countries around the world have come together over several decades to build this machine. What we do is we accept...
So, by the way, this TED Talk is in 2008, and if you watch the whole thing, he talks about the Higgs boson and that they're trying to discover it. And then now we watch in the news, and they've discovered it, right? Like, super cool.
Is this guy like one of the head dudes?
Yes, very much so.
Accelerate protons, so hydrogen nuclei, around at 99.999999% the speed of light. Right, at that speed, they go around that 27 kilometres 11,000 times a second. And we collide them with another beam of protons going in the opposite direction. We collide them inside giant detectors. They're essentially digital cameras. And this is the one that I work on, Atlas. You get some sense of the size. You can just see these EU standard size people underneath. You get some sense of the size. 44 metres wide, 22 metres in diameter, 7,000 tonnes. And we recreate the conditions that were present less than a billionth of a second after the universe began, up to 600 million times a second inside that detector. You know, immense numbers. And if you see those metal bits there, those are huge magnets that bend electrically charged particles so we can measure how fast they're travelling. This is a picture about a year ago. Those magnets are in there, and again, an EU standard size real person, so you get some sense of the scale. And it's in there, those mini Big Bangs will be created sometime in the summer this year. And actually this morning I got an email saying that we've just finished today building the last piece of Atlas. So as of today, it's finished. I'd like to say that I planned that for TED, but I didn't. So it's been completed as of today. Yeah, it's a wonderful achievement. So you might be asking, why? Why create the conditions that were present less than a billionth of a second after the universe began? Well, particle physicists are nothing if not ambitious. And the aim of particle physics is to understand what everything's made of and how everything sticks together. And by everything, I mean, of course, me and you, the Earth, the Sun, the 100 billion suns in our galaxy, and the 100 billion galaxies in the observable universe. Absolutely everything. And you might say, well, okay, but why not just look at it? You know, if you want to know what I'm made of, let's look at me. Well, we found that as you look back in time, the universe gets hotter and hotter, denser and denser, and simpler. Now, there's no real reason that I'm aware of for that, but that seems to be the case. So way back in the early times of the universe, we believe it was very simple and understandable. All this complexity, all the way to these wonderful things, human brains, are a property of an old and cold and complicated universe. Back at the start, in the first billionth of a second, we believe, or we've observed, it was very simple. It's almost like, imagine a snowflake in your hand and you look at it and it's an incredibly complicated, beautiful object. But as you heat it up, it'll melt into a pool of water and you would be able to see that actually it was just made of H2O, water. It's in that same sense that we look back in time to understand what the universe is made of. And as of today, it's made of these things, just 12 particles of matter stuck together by 4 forces of nature. The quarks, these pink things, are the things that make up protons and neutrons, that make up the atomic nuclei in your body. The electron, the thing that goes around the atomic nucleus, held around in orbit, by the way, by the electromagnetic force that's carried by this thing, the photon. The quarks are stuck together by other things called gluons. And these guys here, the weak nuclear force, probably the least familiar, but without it, the sun wouldn't shine. And when the sun shines, you get copious quantities of these things called neutrinos pouring out. Actually, if you just look at your thumbnail, about a square centimetre, there are something like 60 billion neutrinos per second from the sun passing through every square centimetre of your body. But you don't feel them, because the weak force is correctly named. Very short range and very weak, so they just fly through you. And these particles have been discovered over the last century, pretty much. The first one, the electron, was discovered in 1897. And the last one, this thing called the tau neutrino, in the year 2000, actually, just, I was going to say just up the road in Chicago. I know it's a big country, America, isn't it? Just up the road. Relative to the universe, it's just up the road. So this thing was discovered in the year 2000, so it's a relatively recent picture. One of the wonderful things, actually, I find, is that we've discovered any of them when you realise how tiny they are. You know, there's a step in size from the entire observable universe. So 100 billion galaxies, 13.7 billion light years away. The step in size from that to Monterey, actually, is about the same as from Monterey to these things. Absolutely exquisitely minute, and yet we've discovered pretty much the full set. So, one of my most illustrious forebears at Manchester University, Ernest Rutherford, the discoverer of the atomic nucleus, once said, all science is either physics or stamp collecting. Now, I don't think he meant to insult the rest of science, although he was from New Zealand, so it's possible. But what he meant was that what we'd done really is stamp collect there. Okay, we've discovered the particles, but unless you understand the underlying reason for that pattern, you know, why it's built the way it is.
Do you want to watch the rest?
Yeah.
You like it?
Yeah.
Really, you've done stamp collecting, you haven't done science.
If you guys find it interesting,
Fortunately, we have probably one of the greatest scientific achievements of the 20th century that underpins that pattern. It's the Newton's laws, if you want, of particle physics. It's called the Standard Model. Beautifully simple mathematical equation.